Hello, Dan here from howtomechatronics.com. In this video, we will learn about electric flux and Gauss's law. In order to understand Gauss's law, first we need to understand the term electric flux. Electric flux is the rate of flow of electric field through a given surface. It is the amount of electric field penetrating a surface, and that surface can be open or closed. First, we will take a look at an example of electric flux through an open surface. These red lines represent a uniform electric field. We will bring in that field a rectangle, which is an open area, and we will divide the area into very small elements, each with size dA. dA is called the differential of area. Now we are going to make the area dA a vector, with a magnitude dA. The vector direction is always perpendicular to the small element dA. The electric flux that passes through this small area, d phi, also called a differential of flux, is defined as a dot product of the magnitude of the electric field E and the magnitude of the vector area dA times the angle between these two vectors θ. The total flux is going to be the integral of d phi, or the integral over the entire area of E dot dA. It is a scalar quantity and the end result can be positive or negative. If the flux is going from the inside to the outside, we can call that a positive flux, and if it's going from the outside to the inside, that's a negative flux. The unit of electric flux is Newton meters squared per coulomb. To get a better understanding of what electric flux is, I will bring into this electric field three rectangles. In fact, these rectangles represent one rectangle with different orientations. Now let's explain the flux through each one of those open areas. In the first case, the area is perpendicular to the electric field and the angle between their vectors θ is 0. Cosine of 0 is 1, so the electric flux is going to be E times dA. Here we have the maximum flux. In the second case, the angle between E and dA, θ, is 60 degrees and cosine of 60 degrees is 0.5, so the electric flux will be half of E times dA. In the third case, the area is parallel to the electric field, which means that their vectors are perpendicular to each other, and the angle θ between them is 90 degrees. Cosine of 90 degrees is 0, so the electric flux here will be 0. This means that nothing goes through this rectangle, so the flux is 0. Now let's take a look at a surface that is completely closed. How do we define flux? Here we can put some normals, dAs, in different directions. By convention, the normal to the closed surface always points from the inside to the outside. Now we can calculate the total flux going through this closed surface. The total flux is equal to the integral of d phi over the entire surface, which we write as the integral over the closed surface of E dot dA. The total flux can be positive, negative, or equal to 0. If the same amount of flux is entering and leaving the surface, we have 0 total flux. If more flux is leaving than entering the surface, then the total flux is positive. Opposite, if more flux is entering than leaving the surface, we have negative total flux. Let's take a look at another example and see how the electric flux is related to Gauss's law. We have a point charge plus q in the center of a sphere with radius r. Now we will take a small segment dA, which vector is perpendicular to the surface and is radially outward. The electric field generated by Q at this point is also radially outward. This means that dA and E anywhere on the surface of this sphere are parallel to each other, and the angle between them, θ, is 0 and cosine of 0 is 1. The differential of flux through the small surface area, d phi, is equal to E dA. The total flux phi is going to be the integral of d phi, which is the integral over the closed surface E dA. The magnitude of the electric field everywhere is the same because the distance from the charge is the same at each point, so we can pull that out of the integral and we are left with E times A. The total area of the sphere is 4 pi r squared, and the total flux through this closed surface is simply E times 4 pi r squared. From the previous videos, we know that E is equal to K times Q divided by r squared, which is equal to Q divided by 4 pi epsilon naught r squared. Here we can cancel out 4 pi r squared and we can notice that the total flux is equal to Q divided by epsilon naught, where epsilon naught is the permittivity of free space. The flux doesn't depend on the distance r, we would get the same result no matter the size of the closed surface around the point charge. What if we bring more charges inside the closed surface? The equation should also hold for any system of charges inside. This leads us to the Gauss law, which says that the electric flux going through a closed surface is the sum of all charges Q inside the closed surface divided by permittivity of free space epsilon naught. If the flux is zero, that means there is no net charge inside the shape. There could be positive and negative charges inside the shape, but the net is zero. No matter how weird the shape, Gauss' law always holds, as long as there is a perfect symmetry in the charge distribution inside the surface. So, in order to calculate the electric field, you need a symmetry, and there are three types of symmetry: spherical, cylindrical, and planar symmetry. We will start with the spherical symmetry. This is a thin hollow sphere with radius r, and we will bring a positive charge q into the thin shell, which is uniformly distributed. Now we need to find the electric field inside the sphere at a distance r1 from the center and outside the sphere at a distance r2 from the center. To do that, we need to determine our Gaussian surface. In this case, we will choose concentric spheres as Gaussian surfaces, one smaller with radius r1 and other larger with radius r2. Now we need to use two symmetry arguments that will help us calculate the electric field. The first symmetry argument shows that the magnitude of the electric field is the same at any point, since the charge here is uniformly distributed. The second symmetry argument shows that if there is an electric field, it must point either radially outwards or radially inwards. In this example, we have a positive charge, which means that the field is pointing outwards. From the previous equations, we know that the surface area of a sphere, which is 4 pi r squared times the magnitude of the electric field E, is equal to the charge inside the sphere Q divided by the permittivity of free space epsilon naught. However, we don't have a charge inside the smaller sphere, so the electric field is zero. If a closed surface has no net charge enclosed by it, then the net flux through it will be zero. Now let's see what happens with the larger sphere. The symmetry arguments hold for this sphere as well. But if we take a look at the equation, we will notice that Q is not zero, because there is a charge inside that sphere. So the magnitude of the electric field will be equal to the charge enclosed divided by 4 pi epsilon naught r2 squared. If we draw a graph with the distance on the x-axis and the magnitude of the electric field on the y-axis, we can notice the following. Up to the point r, which is the radius of our initial sphere, we have no electric field, but then it reaches its maximum value and decreases as the distance increases. The second type of symmetry is cylindrical symmetry. Let's say we have an infinite line of positive charge with uniform linear charge density lambda, and we want to figure out what the electric field is at some point above the line at distance r. Here we will choose a cylinder as a Gaussian surface with a center along the line of charge. We don't have an electric field through the end caps. The electric field will be pointing out through the walls of the cylinder. Also, we have symmetry here, which allows us to use the Gauss law in order to calculate the electric field. We can calculate the flux using the same equation that we used previously. But now we need to find the surface area around the cylinder, including the wall, without the end caps. For that purpose, we need to cut the cylinder along its length, and we will find out that the area is equal to 2 pi rl. So 2 pi rl times E is equal to the charge enclosed divided by epsilon naught. The charge density lambda is the total charge Q per length L, so the charge enclosed is equal to lambda L. So 2 pi rle is equal to lambda L divided by epsilon naught. The electric field is equal to lambda L divided by 2 pi rl epsilon naught. L cancels out, so the electric field is equal to lambda divided by 2 pi r epsilon naught. The last type of symmetry is planar symmetry. In this example, we have a flat infinite large horizontal plate. We will bring a charge onto this plate with a uniform charge density sigma. Sigma is actually an amount of charge per area and is expressed in coulombs per squared meter. Now we want to calculate the electric field in the surrounding area of this plate, let's say at a distance d. In this case, we are going to choose a cylinder again as a Gaussian surface. The cylinder intersects the plate, and in that intersection we have a charge enclosed. In order to be able to calculate the electric field, we need to meet three conditions. First, the cylinder end caps with an area A must be parallel to the plate. Second, the walls of the cylinders must be perpendicular to the plate. Third, the distance from the plate to the end caps D must be the same above and below the plate. Now that we met the symmetry requirements, we can calculate the electric field using the Gauss's law. We are not going to have any horizontal components of the electric field, only vertical coming out of the two end caps. Sigma is equal to the charge divided by the surface, and from this equation we can see that the charge Q is equal to sigma times the area. The flux from the wall of the cylinder is equal to 0, so the total flux consists of two components, the flux through the top cap plus the flux through the bottom cap of the cylinder. This is equal to Q enclosed divided by epsilon naught, or sigma A divided by epsilon naught. But also the flux through the top and the flux through the bottom can be expressed as EA, so the total flux is equal to 2EA. Finally, the electric field is equal to sigma divided by 2 epsilon naught. If the plate is positively charged, the electric field would be pointing outward, and if it is negatively charged, the electric field will be pointing inwards. If we draw a graph with the distance d on the x-axis and the electric field on the y-axis, we can notice that the electric field has a constant value of sigma over 2 epsilon naught, and it doesn't depend on the distance from the plane. Now let's take a look at another more complex situation of two infinitely large parallel plates. The first plate has a surface charge density plus sigma, and the plate below has a surface charge density minus sigma. The distance between them is d, so what is the electric field anywhere in the space? The positively charged plate has an electric field pointing away from the plate, equal to sigma divided by 2 epsilon naught. It doesn't depend on the distance from the plate, so it continues below. The negatively charged plate has an electric field pointing towards the plate, also equal to sigma divided by 2 epsilon naught. In order to calculate the total electric field, we are going to use the superposition principle by adding vectors. The vectors that are in the opposite direction cancel out, so the electric field there is 0. The vectors between the plates are in the same direction, so the electric field is sigma divided by epsilon naught. Here's how the electric field lines would look like. They will be pointing away from the positively charged plate and towards the negatively charged plate, and the electric field outside will be 0. Okay, so that would be all for Gauss's law. I hope this video was helpful and you learned something new. Don't forget to subscribe, and for more tutorials visit my website howtomechatronics.com.